All right, let's talk about something that sounds like science fiction but is very real and very important. Homomorphic encryption. This is the cryptographic key, pun intended, to a future where we can use powerful AI without having to give up our privacy to do it. So think about the big problem we all face. We want to use these amazing AI tools that live in the cloud, right? But that means we have to hand over our data, sometimes our most sensitive personal information. It's always felt like this unavoidable trade-off. You get the smart analysis, but you lose your privacy. But what if that trade-off just vanished? What if a model could process your data while it stays completely encrypted, totally unreadable to anyone but you? Well, that is exactly the promise of homomorphic encryption, or HE. Now, the formal definition on screen is a mouthful, but the actual idea is surprisingly simple. My favorite analogy is the lockbox. Imagine you put your sensitive data into a locked box. You send that locked box to a service provider. They never get the key. They can't see inside, but they have special tools that let them work on the contents through the walls of the box. When they're finished, they send the box back to you, and only you, with your key, can open it up and see the result. They did all the computation, but they never saw your data. That's really it. That's HE. Now, you might think this sounds completely backwards. I mean, encryption is supposed to scramble data to make it useless, while machine learning needs to find patterns in that data. The fact that these two can work together so effectively is, frankly, a huge breakthrough. It's this amazing synergy that's really opening the door for private AI to become reality. So, let's get practical. How does this actually look when you're building a system? The process is called encrypted inference. This is where all that cool crypto theory meets the real world of engineering. It really boils down to a pretty straightforward three-step dance. First, encrypt. Your data gets encrypted right there on your own device, your phone, your laptop, before it even touches the internet. Second, compute. That encrypted data, which we call ciphertext, gets sent to the cloud. The AI model does its thing, it runs its calculations on this scrambled data. The whole time, the cloud provider sees nothing but gibberish. And finally, third, decrypt. The encrypted answer comes back to your device, and only you have the key to unlock it and see the final output. Your data stays private from start to finish. Okay, I know this sounds a bit like magic, but as an engineer, my job is to live in the world of trade-offs, and each E has them. It's not some silver bullet that works for everything, at least not yet. So let's dig into where it really shines today and what the big challenges are. A perfect example of a natural fit is something like linear regression. It's a really common machine learning model, and at its heart, it's all just simple math, adding things and multiplying things. Well, it just so happens that those are the exact operations that work beautifully with most homomorphic encryption schemes. So for a whole class of models like this, HE is already a practical, ready-to-go tool. It's a really intuitive win. But things get a lot more complicated when you move to something like a deep neural network. The math inside those models often involves things that are really, really hard to do on encrypted data. Things like comparing two numbers or using nonlinear functions. So a huge part of the work right now is actually redesigning the AI models themselves. We have to find clever ways to swap out those HE-unfriendly operations and approximate them using only the math that works, like addition and multiplication. And that leads to another massive engineering challenge: precision. You see, with every single mathematical operation, most HE schemes introduce a tiny amount of noise. If you're only doing a few calculations, it's no big deal. But a neural network does thousands, sometimes millions of them. That noise accumulates, it builds up, until your final answer is just, well, it's garbage, completely useless. So a huge part of the job is carefully tuning the cryptographic parameters to keep that noise under control. You're in a constant battle to make sure the answer is not only private, but also accurate. Now, these challenges aren't deal breakers, not at all. They're the cutting edge. This is where all the active research and development is happening. The core ideas are proven. Now, it's all about making it faster, better, and more scalable. Let's look at what's coming up on the horizon. Right now, the #1 hurdle is performance, plain and simple. Doing math on encrypted data can be orders of magnitude. We're talking hundreds, even thousands of times slower than doing it on regular data. So the entire field is laser-focused on one thing: optimization. From designing custom computer chips to writing better software, the race is on to close that performance gap and make private computation fast enough for the real world. And that really brings us to the final big picture idea here. As we keep chipping away at these engineering problems, the possibilities are just staggering. Think about it. Multiple hospitals could train a shared AI model on all their patient data to fight disease without a single private record ever being exposed.
Financial institutions could collaborate to detect massive fraud networks without ever sharing sensitive customer information. So the question I'll leave you with is this. What new worlds open up when that fundamental conflict between getting valuable insights and protecting our privacy just goes away?